Good evening, everyone, and welcome to the Longmont Museum. My name is Eric Mason. I'm the director of the museum, and we are delighted to be presenting another wonderful program tonight. Before we get started, I would like to thank the folks who made this possible: the City of Longmont, the Scientific and Cultural Facilities District, the Stewart Family Foundation, the Friends of the Longmont Museum, and of course, our museum members. Do we have any members of the museum here tonight? Thank you so much. We could not do what we do without your support. I'd also like to thank our media sponsors, KGNU Community Radio, and KUNC, and the Colorado Sound. Tonight's program is offered as part of our ongoing Thursday Nights at the Museum series. Every Thursday night, we offer up a film, a concert, a talk, or a performance. We have a little something for everyone. There's often a connection to our special exhibition. Right now, we have a wonderful special exhibit on the prints of Pablo Picasso. If you haven't had a chance to see it, it is running through May, so you have a few more weeks to check it out. Tonight, we are delighted to team up once again with our friends at the NSF National Center for Atmospheric Research, or NCAR, for another installment of their Explorer series, which touches on the pivotal areas of NSF NCAR research, such as weather, natural disasters, ocean currents, air pollution, and the behavior of the sun. Some presentations deal with atmospheric issues that directly impact folks right here in Colorado, such as tornadoes, while others look at atmosphere and science on a global level, like the one tonight. Tonight's program, Keeping an Eye on the Sun's Magnetism, will be presented by Dr. Rebecca Centeno Elliott, who is a project scientist with the High Altitude Observatory at NSF NCAR. Dr. Centeno uses her background in physics and astrophysics to research the magnetic forces within the sun that cause solar storms. These impulsive events, as she describes, happen when the sun releases material and radiation into space. Solar storms can interfere with satellite navigation, radio communication, and even disrupt the electric power grid. Dr. Centeno enjoys research because she describes it as a puzzle and says you have to search for the pieces and figure out how to put them together. Please welcome Dr. Rebecca Centeno to the Longmont Museum.
Thanks for the kind introduction, and thank you all for being here and for being curious about the sun today. And thanks to the Longmont Museum and to the NCAR Explorer series, because I believe that talking to the public about the science that we do is also a very important job. So today I'm going to be talking about keeping an eye on the sun's magnetism, and you'll see why. So the sun is a star, and that doesn't surprise any of you. It's a pretty ordinary star, mediocre in fact. It's not very big, it's not very small, it's not very bright or very dim or very hot or very cold in the big context of all the stars and objects in the universe. It's a pretty boring object to study. Yeah, tell that to my nighttime astronomer friends. They always just roll their eyes at me and they're like, why would you spend your entire career looking at the sun? But the sun, of course, is special to us. It does provide the light and the heat that sustain life on Earth. Now, the sun is about 4.5 billion years old. It's somewhere in its midlife right now. And although towards the end of its life, like in another 4 or 5 billion years from now, it will expand to engulf the inner planets in the solar system, that's still a really long time away. And right now it's enjoying a pretty stable and uneventful phase in its life. But the sun changes. It changes every second of every minute of every day. It changes in ways that we are able to measure, and it changes in ways that actually affect us. And that is the topic of my talk today: how the sun changes, what causes those changes, and how those changes affect us, and how we want to learn about them. So I'm going to kick it off with a poll, because that's what you do at public talks. Can anybody tell me what you think this picture is? Go ahead. Sunspots, exactly. So that is a picture of the sun taken by NASA's Solar Dynamics Observatory. That's the surface of the sun that you see in there. And yeah, those dark things are sunspots. This great quality picture. Any guess? Almost. It was way after sunset. Yeah, so the reason it's poor quality is that I took it outside of my front yard with my phone in gun barrel just a few miles away from here. It was the northern lights that were visible in Colorado last October. I was very, very excited because it was my first time. We don't usually see them this far south. Come on, you know. Yeah. So this is a solar eclipse. So what it is a picture of the moon that's sitting in front of the disk of the sun and blocking most of the light that comes from the sun. And when you block all the light from the disk of the sun, then the outer atmosphere of the sun becomes visible, and that's the solar corona. So those rays that kind of fan in outwards in all directions, that's part of the outer atmosphere of the sun. It's called the solar corona. So I'm going to straight to it in lecture mode. This is definitely not the most interesting slide, but it gives you a little bit of context of what we know about the structure of the sun. So you might want to think as the sun as an onion or something with layers, right? And in each one of these layers, different physical processes dominate. So you have the very inside of the sun's core, and there the temperature is so high. The pressure and the density are so high that it's like a nuclear fusion reactor. So nuclear reactions are taking place all the time, and you have hydrogen atoms that combine to form helium, and when this happens, they release energy in the process, typically energy in the form of particles of light, of photons. Now, as this energy travels outwards, it goes through a next layer of the sun. It's called the radiative zone, and there the density is still so high that it takes that energy about 1 million years to escape that region. And once it escapes it, it reaches the next layer of the interior of the sun. This is called the convection zone. And energy here propagates outwards by means of convection. You know convection. Convection is what happens when you put a pot of water on a hot stove, and you have the stove heat up the bottom of the pot. The water heats up, it expands, it becomes buoyant, it rises to the top of the pot, and when it reaches there, it releases that heat that it gathered at the bottom. As it releases heat, it becomes colder again, it plummets back in. And it creates this cyclic behavior by which hot water at the bottom rises to the top, releases heat, and plummets back down. And this is, in essence, a way of propagating that heat from the bottom to the top of the pot. So that's what happens there. Now, the top of that convection zone marks the end of the sun's interior and the beginning of the sun's atmosphere. Now, the sun doesn't have a solid crust like the Earth, so it's a gas, essentially, or a fluid throughout, and the end of the sun's interior is not delineated by a solid crust that separates from the gaseous atmosphere, right? In fact, what delimits the sun's interior from its atmosphere is that the interior is opaque. We don't see any light from it. The first layer of the sun's atmosphere, that one right there, is what we call the photosphere, is the layer of the sun from which most of the light that we see comes from. So if you were to go outside right now, if it's not after sunset, and you were to look at the sun directly right now, which you shouldn't do, of course, but even with a filter, what you see when you look at the sun through a filter right now is the photosphere of the sun. That's where the vast majority of the light is coming from. Above that, there's a thin crust that we call the chromosphere, and then even above that is the sun's corona, the one that we saw earlier in the solar eclipse. Now the corona is this very, very tenuous and very large part of the sun's atmosphere. It actually extends millions of miles into space. Humans realized a long time ago that the sun was not this perfect, immaculate object, that in fact it was dotted with like dark spots that kind of moved around. The first record of sunspots, or the first written record at least, goes back more than 2,000 years. But it wasn't until the early 1600s or so when humanity invented the telescope that kind of really turned around the world of astronomy, that astronomers started to take consistent notes about sunspots. They started taking like consistent records, noting their appearance, their location, their evolution on the sun. But back in those days, astronomers didn't really know what sunspots were. They thought, well, some of them thought that they were just shadows of undiscovered planets that were transiting in front of the sun's disk. Some thought they were clouds in the sun's atmosphere itself, casting shadows. Today, we know that sunspots are part of the sun, and they're magnetic in nature. They appear dark because of the strong magnetic forces inside them. Very, very strong. So magnetic forces that are generated in the interior of the sun sometimes protrude through the sun's surface and into its atmosphere, and the places where these magnetic forces intersect the sun's surface, that's where sunspots appear. So sunspots are dark because they are cold, or at least cold relative to their surroundings. And they're colder than their surroundings because these very strong magnetic forces inside them inhibit the propagation of heat towards the surface. Now, sunspots are not cold in absolute terms. Even the coldest of sunspots can still melt the hardest metal to melt on Earth. Tungsten, I learned from Wikipedia. Just briefly, let me digress a little bit and talk about magnetic forces. So throughout this talk, I'm going to be mentioning magnetism, magnetic force, magnetic fields, magnetic lines of force, but for all intents and purposes, all of these words, terminology, mean the same thing. And it refers to the same forces that happen when you attach a magnet to your refrigerator door. So a magnetic force is a force that is generated when you have an electrically charged particle, like an electron or an ion, that is in motion, that moves. Just because it moves and it's electrically charged, it generates a magnetic force. This force is very intricately related to electricity and electric forces. So when you have an electric particle moving, it creates a magnetic force. When you have a magnetic force changing in time, that can create an electric field and induce an electric current if there happens to be a charge there. Why is this relevant, you may ask? Well, the sun, I think I said the sun was a gas. The sun is a plasma. A plasma is just like a fluid, but it's composed of a mix of neutral and electrically charged particles together. And because the plasma on the sun is constantly moving and churning, and there's flows, those electrically charged particles are moving. And when they move, they generate magnetism. So magnetism on the sun is constantly being generated and destroyed and amplified and changed all of the time. All right, so the lifetime of a given sunspot is typically a few weeks, anywhere between a few days and a few months. Now, at any given time, the number of sunspots on the sun's surface is not constant. That video right there are observations, again, by an instrument on the Solar Dynamics Observatory of the sun's surface over the course of a few months. Actually, no, a few years. And what you can see is that the number of sunspots on the sun's surface waxes and wanes over an 11-year period. If you look at the graph on the left, each dot on that graph represents the number of sunspots counted over the course of a month, from the year 1900 on the very left to the year 2025, towards the right of the figure. And what you see there is that the number of sunspots, yes, is not constant. There's a lot of variability, but there's a strikingly strong pattern that repeats itself every approximately 11 years. And this pattern has been repeating itself not since the year 1900, but since we started observing sunspots routinely, at least. This is what we call the solar cycle, that 11-year period in which sunspots go from a minimum number all the way to a maximum and go back down to a minimum. And some solar cycles are larger than others, some solar minima are deeper than others, but essentially this pattern keeps repeating itself over and over again. And sunspots are not the only thing to change over this 11-year period. The amount of radiation or light that the sun emits changes over an 11-year time span. In the same way, the number of solar storms, which we'll see a little bit more about them later, also varies over this 11-year time frame. So that figure is showing pictures of the sun in ultraviolet light. So this is the light the sun emits in ultraviolet. From 1996 all the way to 2006. 1996 and 2006 were solar minima, when there's few sunspots on the sun. 2001, down at the center, it was a solar maximum, when there were most sunspots on the sun during that specific solar cycle. And you can see the pattern. During solar minima, there's less ultraviolet emission. During solar maxima, there's a lot more ultraviolet light that comes from the sun. The same happens with the number of flares. In this graph, each bar represents the number of flares, or solar flares, that have happened over the course of that year, from 1997 to 2007 in this case. Similar time frame, I just couldn't find the right graph. A flare is a type of solar storm. And you can see that in 1997 and 2007, which are very close to the solar minimum, the number of flares was low, and during the maximum years, the number of flares is really high. This is no coincidence. Number of flares are associated to sunspots, and they're associated to magnetism. Space weather. You might have heard this term in the news, or maybe not, but space weather refers to the changing conditions on the sun and how they affect the interplanetary medium, the space in between the planets. And we're, of course, particularly interested in how space weather affects near-Earth space. And space weather, just like weather on Earth, has a variety of different phenomena associated to it, from the constant buffeting of the sun's wind, the sun expels the wind outwards all of the time, to the different solar storms events that it might experience. Solar storms, just like Eric said at the introduction, are impulsive events in which the sun releases vast amounts of mass, energy, radiation, and magnetism into space that can travel through space at really high speeds. We're going to see a few examples of those. That little puff is something that we call a coronal mass ejection, or CME. A coronal mass ejection is like this huge bubble of solar plasma that is threaded with magnetism throughout, that is expelled from the sun's surface over the course of several hours. A powerful CME can expel the equivalent of the mass of Mount Everest and launch it at high speeds through space, at speeds of millions of miles per hour. This one is highly related. This is a filament eruption, oftentimes part of CMEs. A filament was that dark, elongated structure that you saw at the beginning of the video. If I can get it to play again. That one there, that thing. That's a filament. A filament is a large concentration of dense solar material that is suspended above the sun's surface. And it's not falling down back to the sun's surface because there's magnetic forces that are holding it up in place. And that filament could have been there for weeks or even months, just stably suspended above the sun's surface. But as the motions of the plasma in the sun's surface twist and stretch, and build up energy in that magnetic structure that is holding that filament, they will drive it to a state of imbalance, and these magnetic forces that are supporting it will just snap and release all of that mass and excess energy that was stored inside it. That's a solar flare. A solar flare is just a very sudden brightening, and usually very short-lived, that happens in the sun's atmosphere. And when this happens, the sun emits very much enhanced X-ray and extreme ultraviolet radiation. And flares are typically associated to sunspot regions. Again, not a coincidence. Now, these flares and coronal mass ejections and filaments, all of these things oftentimes come together, but sometimes come separately, and they're different space weather flavors, so to speak. The sun's magnetism is not confined to sunspots, and it's not confined to the surface of the sun. It actually extends out into space in all directions, and gives rise to something that we call the heliospheric magnetic field. Now, this magnetic field permeates the entire solar system, and it's dragged around by the sun's wind. Now, the heliospheric magnetic field also serves a purpose to provide sort of pathways along which some of these space weather events tend to travel. And just to show you that it is magnetic in nature, this picture, again, a picture of a solar eclipse, right? It's a picture of the light emitted by the corona of the sun. So it's just a picture of light, but that light is arranged where the material in the corona is. And the material in the corona is arranged along those like curved, quasi-curved lines that are characteristic of the magnetic lines of force. So the material in the sun's corona is following the magnetic field. The Earth has a magnetic field of its own. It's called the magnetosphere. And it provides this protective bubble around our planet that shields us from the effects of the solar wind and from the effects of space weather. The place where the Earth's magnetic field meets the heliospheric magnetic field that comes from the sun is called the magnetopause. And at the magnetopause, the Earth's magnetic field points north. Okay. The heliospheric magnetic field, on the other hand, can point in principle in any direction. And when it happens to point southwards, those two magnetic fields cancel out. And it peels off some of these protective layers around our planet. And when that happens, the energetic particles that come from the sun have a less hard time penetrating into the Earth's magnetosphere. And this is how space weather begins to affect us. So one of the most awe-inspiring effects of space weather, and a much better picture than the one I took, is aurora, the northern lights or the southern lights. And these happen when the Earth's magnetosphere, that magnetic bubble, gets disturbed and energized by forces that come from the sun. And when it gets energized, it kind of energizes the particles that sit trapped in that magnetic jail, and it accelerates them. And they're accelerated in a way that they follow the magnetic field lines of the Earth straight into the poles of the Earth, or the polar caps of the Earth. And as these particles enter into the Earth's atmosphere, they collide with the atoms and the molecules that are present there. And these atoms and molecules in turn emit little bursts of light of very specific colors. And all together, those bursts of light comprise the aurora. But the effects of space weather on Earth can be multiple. And mostly space weather tends to affect technology in near-Earth space. So for instance, energetic particles from the sun have the capability to penetrate satellite electronics, causing electrical failures in satellites. They are also a hazard for astronauts that are in space, because they can cause increased risk of cancer and even radiation sickness. So when powerful events from the sun happen, astronauts in space must take cover behind protective shields to not get affected by radiation exposure. But even aircraft on Earth that fly over the Earth's poles, those routes might get rerouted in case of, at times when there's excess solar radiation coming in, particles coming in through the poles. Solar flares, those brightenings that emit X-ray and ultraviolet radiation, they actually perturb the Earth's ionosphere. The Earth's ionosphere is a layer in the Earth's atmosphere that is very important in radio communications. So when it's highly disturbed, it actually degrades radio communications or even causes radio blackouts at times. It also has the effect, that radiation, that light, that X-ray and ultraviolet radiation has the effect of expanding the Earth's thermosphere. This is a big layer of the outer Earth's atmosphere. And as it expands, it increases the density in lower Earth orbit, where there's a lot of satellites revolving around the Earth. And when this density increases, it increases the drag that the satellite experiences as it orbits around the planet. And an increased drag results in a decreased speed, and when the speed decreases, they slowly deorbit. Okay. Then there's something called geomagnetic storms. So when we have a coronal mass ejection that ejects magnetism into space and interacts with the Earth's magnetic field, it causes something that is called a geomagnetic storm. That's a disturbance in the Earth's magnetic field. And when the Earth's magnetic field is disturbed and changes, then it can cause induced currents on power lines on the ground, and therefore degrade power grid operations. And another thing that Eric mentioned at the beginning, solar storms also have the effect of degrading GPS or other navigation system signals, which might not be super important to us, but small degradations of GPS signals are very important for industries that depend on high accuracy location services, for instance. So all of these are not just theoretical. I went to Google and I pulled from different news stories related to solar storms and how they've affected technology in different ways. The one on the left-hand side is a story that happened in 2022 when SpaceX launched for, a number of Starlink satellites into lower Earth orbit. And some of those satellites were, I think they were just waiting in some sort of intermediate orbit and doing some testing before going to the final orbit higher up. But a solar flare happened and it expanded that thermosphere. The satellite drag increased and all these little satellites kind of deorbited and so plunged back down into the Earth's atmosphere and burnt up in the atmosphere of the Earth. There's one example of a geomagnetic storm. I don't think I can move my cursor. In 1989, where a big geomagnetic storm caused by a coronal mass ejection disrupted the electricity transmission system in some parts of Canada. It ground to a halt the operations of the Hydro-Quebec power system, and that left about 6 million people without electricity for about 9 hours. The last one here, I put it up because I thought I watched the talk a few years ago and I thought it was very curious. It's maybe anecdotal at this point, but it's a story that was uncovered by my colleague Dolores Knipp at CU with her collaborators, and they discovered that in 1967 there was a solar storm that almost brought the US to the brink of war with the Soviets. This was at the height of the Cold War. There was a big solar flare, disrupted radio communications big time, and the first thought went straight to the Soviets. They're like, the enemy is messing with our communication systems, and it was only because there was some very smart people that kind of knew about the sun a little bit, and they were like, wait a second, we might want to wait to see whether these radio disruptions go away within the next hour. We maybe should hold back in launching an attack. And they finally figured out that it was the sun, in fact, and it was not the Russians that were trying to mess with communications. That I don't think would happen nowadays, but it's interesting. All right, so how are all these things connected? Well, I think you have the answer. Magnetism. Magnetism on the sun allows the sun to build up energy and hold mass in these super complex and unstable configurations. And when those configurations are led to a state of imbalance, they kind of like erupt, rupture, and send out into space all that mass and energy that was stored inside them. And again, the magnetism also provides those pathways throughout the entire solar system for some of these events to travel along. How do we measure the sun, and in particular its magnetism? Well, as you know, we don't have the technology to send probes directly into the sun to go and measure these things. We use remote sensing to learn about the sun. And remote sensing is the science of identifying and measuring an object without coming into direct contact with it. We do remote sensing every day in life. Usually happens through either sound or light. And solar physics, just like the rest of astronomy, is pretty much a science based on remote sensing. We measure light. And from the light, we infer information about the physical conditions in the sun. We learn about its temperature, its pressure, its density, its magnetism, its flows. But we measure light. The way we measure light, we need three basic components, right? Telescopes. Telescopes capture the light and magnify the image. Instruments. The instruments analyze the properties of that light that we're capturing. And then, of course, some form of detector to record that light. And then hand it out to scientists to analyze. Telescopes. Telescopes are arrangements of mirrors and lenses that capture the light from the sun and magnify that image. If we were to look at the sun with a naked eye, again, never, but if we were to look at the sun with a naked eye, we'd see it subtends a angle in the sky of about 0.5 degree. This is the angle from your eyes to the disk, the edges of the disk of the sun, about 0.5 degree. Our eyes are able to discern anything that subtends an angle of 0.02 degrees, much smaller than that. Our eyes are able, in other words, our eyes are able to see something that's about this big. That's 0.5 mile away, if you have a good eye, not like mine. So, because the sun subtends a much bigger angle, we're able to see not only the disk of the sun, but we should be able to see details on it. And in fact, if there is a large group of sunspots on the sun's surface, and you go out and look at them through eclipse glasses or something like that, without magnification, you should be able to see those sunspots. Not in detail, but you should be able to see them. The sun is the only star that we're able to resolve, that's the word. All the other stars in the nighttime sky, we only see as points. So with the aid of telescopes, we can actually get to see way more details on the sun. This, again, is an image taken by the Solar Dynamics Observatory, and as we zoom into that image, we can see how much detail we're able to see in that specific sunspot. This is a very small sunspot, so you probably wouldn't be able to see it with your naked eye, without magnification at least. Now, this instrument is able to discern the equivalent of something that's about this big, 0.5 centimeter, at 0.5 mile away, approximately. If we look at the same sunspot with the Swedish Solar Telescope, we can now see a lot more detail. This telescope is able to discern something that's about, I don't know, this big, something less than 1 millimeter big, at a distance of 0.5 mile. So it's like taking the fine print in your cell phone contract, putting it 0.5 mile away and reading it. It's pretty cool. So what determines the spatial resolution of a telescope? The spatial resolution is its ability to see details. What determines its ability to see details? Well, there's many factors that go into it, but the ultimately limiting factor is the aperture of the telescope. The aperture of the telescope is just the physical size of its main mirror or its main lens that's capturing the light. It's just the diameter of that big mirror or big lens. If you double the aperture of a telescope, if you double the size of that mirror, then you get to see details that are half as big. And that's the main reason astronomers are always asking for bigger and bigger telescopes. One of the main reasons. So here's an example of images of the sun's surface taken with 3 different telescopes. The one on the left is a 14 centimeter aperture, so I don't know, something like that. The second one is 70 centimeters. And the last one is the DKIS, the Daniel K. Inouye telescope, which is in Maui, and that's about 4 meters. So it's, yeah, maybe not as big as the screen, but it's pretty big. So what are the advantages and disadvantages of putting telescopes on the ground versus putting them in space? Of course, on the ground, you have nighttime, and that's a pretty big disadvantage. You have a telescope in one location on Earth, and half of the time it's going to be nighttime, no matter what you do. Additionally, even during the day, there's clouds occasionally, right? Adverse meteorological events that don't allow you to see the sun. Putting a telescope in space is very, very expensive compared to putting the same telescope on the ground. And fixing a telescope in space or upgrading an obsolete instrument is nearly close to impossible, at least for most telescopes in space. Yeah, I'll leave it at that. However, even in the best of days, clear skies, when you have a telescope on the ground, the turbulence in the Earth's atmosphere gets in the way of good astronomical observations. So now, imagine that you're sitting, right next to a campfire, and you're looking just above the flames of that campfire to an object in the distance. And you see that object, and that image of that object kind of like flickers and shimmers and gets blurry at times. Well, that's because the light rays that are coming from that object are going through the air above the campfire, and there's hot and cold bubbles of air rising above those flames. And those hot and cold bubbles bend the rays of light in slightly different directions, and then muddle up that information, and you get to see a blurry object. And the same happens with astronomical observations. The light that comes from the sun penetrates through the Earth's atmosphere, and in the Earth's atmosphere you have that turbulence that kind of bends those rays of light and mixes up that information, making the images blurry. So that's one of the reasons to get away from the Earth's atmosphere and put telescopes into space. You get much better quality of images. The other one has to do with the ozone layer. The same ozone layer that protects us from the damaging ultraviolet radiation from the sun is the ozone layer that prevents those ultraviolet rays to actually reach the ground. But it turns out that in that ultraviolet light that the sun emits, there's a lot of diagnostic information that is useful for astronomers to learn about the sun. So the only way to get to measure this ultraviolet light is to go into space. Instruments, the next piece. So instruments, I'm not really going to talk about instruments, but instruments, these devices that furnish telescopes that analyze the properties of the light. And that's what I want to talk about. I want to talk about the properties of the light. So the first 2 properties, very intuitive in many ways. You first have intensity, which our brain and eyes experience as brightness. And then the second one is frequency or wavelength, which our brain and eyes experience as color. Now, our eyes are only sensitive to a small range of wavelengths in the spectrum of light. It's the visible part of the spectrum, and it contains the colors in the rainbow. But there's many other colors of light that we are actually not able to perceive because our eyes are not sensitive to them. And the sun emits all of them. The third property of light is polarization. This is a property of light as a wave, and it's not very intuitive because our eyes are barely sensitive to it. In fact, for the most part, they're non-sensitive to it. So it's a property of light as a wave. Imagine that I'm holding a long rope. I'm going to have to move away from the micro to demonstrate this. I'm holding a rope, and I'm moving my arm up and down like this. and I'm creating a wave in the rope that is propagating outwards towards you. And because I'm moving my arm up and down, the wave is contained in this vertical plane. Now imagine that I move my arm horizontally like this instead. Right? And now I create another wave that is contained in the horizontal plane. Those are linearly polarized waves, the linear polarization. The linear because I'm moving my arm in a line. Now if I take that end of the rope and move my arm in circles like this, I generate a spiral pattern that propagates along that rope. That is called circular polarization. Now, light waves can be polarized in any of these ways or any combination of linear and circular polarization. It can also be unpolarized. This is the equivalent of me taking that rope and shaking my hand in all random directions and not creating an organized pattern of movement. We'll get back to polarization later, but let me talk a little bit about the spectrum of light first. So if you take the light from the sun and you shine it through a prism or something like that, it will spread the light into all of its colors, and you'll get to see the spectrum of the light, all of its colors separated. This is an image of the spectrum of the sun. And if you look at it carefully, it is littered with these dark lines everywhere. Those are called spectral lines. And they're places in the spectrum where light of very specific colors is missing. Spectral lines are the fingerprints of the atoms and the molecules that form the sun's atmosphere. Each type of atom and each type of molecule imprints a very specific pattern of lines in very specific color locations on the spectrum. So just by looking at the spectrum and identifying the patterns of lines that are present in the spectrum, you can learn what are the atoms and the molecules that compose the sun's atmosphere. And you can also learn how many of each type of atom and each type of molecule is present in the sun's atmosphere. But they actually provide more information than that. You can see that some of those spectral lines are broad and very dark, and some of them are very faint and very narrow. The shapes of these spectral lines carry information about the physical conditions in the sun's atmosphere. They carry information about what the temperature is, what the pressure is, what the density is, what the movements of the plasma are. All of that information is carried in these spectral lines. And different spectral lines probe different physical regimes in the sun. Different spectral lines are sensitive to different layers of that onion, if you will. And by observing the sun and measuring the sun in different colors of light simultaneously, you can begin to reconstruct the three-dimensional physical processes, and physical structure of the sun just from its light. A little bit more about polarization. So most sources of light are unpolarized. Again, it's like shaking that rope randomly, right? But there are certain physical mechanisms that polarize the light. The one that we're probably familiar with, and I'm sure that you've all experienced it, is reflections off of shiny, flat surfaces. So you're driving east in the morning. The sun is just above the horizon, right? And it might not be shining directly in your eyes, but the reflection off of the road is killing you. So you reach into your glove compartment, you get your polarized sunglasses, you put them on, and you feel like instant relief. What is happening there? So the light from the sun reflects on this flat, shiny surface, the road, and as it does so, that reflection causes the light to become polarized, and it becomes polarized parallel to the road in the horizontal plane from your perspective. You put your polarized sunglasses on, and the way these work, polarized sunglasses are essentially polarization filters, and the polarization filters such that they block out all of the horizontal polarization, and they only allow the vertical polarization to come through. So the effect of putting your sunglasses on, aside from like reducing the ambient light in all directions, is really canceling out that glare from that flat horizontal surface that is the road. In the sun, the main mechanism that generates that polarized light is the presence of magnetism. So now we have a way to find magnetism on the sun. This is an image that probably I've never seen before, unless you're a solar physicist, it doesn't make any sense to anybody. It's an image of the sun in polarized light. So those white and black splotches are regions of the sun that emit polarized light. And where their image is gray, the light that comes out of those areas is unpolarized or very weakly polarized. And as I mentioned a minute ago, the mechanism that's producing polarization on the sun is magnetism. And magnetism is in sunspots, right? So on the left-hand side, you have just a normal brightness picture of the sun. And if you go and correlate those areas, it is the sunspots and the regions surrounding those sunspots that appear bright in the polarization image. Well, bright or dark. Those are two different flavors of polarization, they're black and white. But there's a very strong correlation. So polarization tells us where there's magnetism on the sun. Now, even if you go to a place on the sun where there's apparently nothing, and you look with a more powerful telescope and a more sensitive instrument, you can see those white and black splotches of polarization everywhere. They appear and disappear, emerge, submerge, and are moved around by the motions of the plasma of the sun's surface. But there's polarization everywhere on the sun at the smallest scales that we are able to observe. There's magnetism everywhere on the sun at the smallest scales we are able to observe. Right, we measure polarization. We measure light, we measure polarization of that light, we measure the colors. How do we interpret these measurements to turn them into a magnetic field? Well, of course, we use theory and equations to do this. And the equation that is relevant to this process of understanding the information that is contained in the light is called the radiative transfer equation. And the form of that equation is irrelevant right now, but this radiative transfer equation describes how light changes as it propagates through a medium, like the sun's atmosphere. It tells us how the intensity and the polarization of the light from the sun change as that light travels through a hot pocket of plasma, or a sunspot, or a strong wind. And the light that comes out of the sun carries the information of the places where it's been, because its intensity and its polarization and its colors have changed as it goes through all these environments. So that equation helps us decipher the information that the light has collected. What I'm going to show you now is just a video of a group of sunspots on the sun's surface and how they change as new magnetism is emerging onto the sun's surface. But it's not an image of the sun. It's not even an image of its polarization. The data have already been interpreted in terms of the magnetic forces. So what you see right here, blue and red now represent magnetic polarities, north and south. And those little lines that look like hedgehogs almost, the directions of those lines of force of the magnetism. We learned that from light. It's pretty cool. All right, then we get to the end of the talk. I've kept you here long enough. What are all these measurements for? Well, first, of course, measurements of the polarization of the light from the sun allow us to identify regions that have strong magnetic fields. We can quantify the strength of those fields. We can measure their direction in space. We can see how they change in time. We can see how they build energy into complex magnetic structures that then might, eventually lead to a solar storm. And in fact, a lot of my colleagues nowadays devote their careers to trying to understand what are the clues in the data that tell us that a solar storm is about to happen. Both long-term knowledge and short-term observations of the sun are very important to understand it. So long-term observations of the sun that happen over the course of decades or even centuries are very important to understand the overall possible variability of the sun's behavior. This here is a very, very long-term record of sunspot numbers going back to the 1600s. It's kind of spotty at the beginning. But you can see, of course, you can see that solar cycle that we talked about earlier, that 11-year period. But on top of that solar cycle, there's variability at much larger timescales too. And we can only learn this from long-term records. Very fast cadence observations, on the other hand, allow us to study in detail these impulsive events like the solar storms or things that happen on short time scales. This video here is a time lapse over the course of a month made from images from the LASCO coronagraph. A coronagraph is a device, it's a telescope device that allows us to observe the sun's corona because it blocks the light from the solar disk. It's like creating an eclipse, kind of, an artificial eclipse. And what you're seeing right there over the course of 1 month is all these like puffs that come out. Those are coronal mass ejections. All right, observations allow us to build and constrain numerical models of the sun. Numerical simulations are computer implementations of mathematical equations or mathematical models that describe a physical system, like the sun. Now, we use computers because oftentimes these equations are too complex to solve with pen and paper and need the processing power of computers. And we need observations because these equations are also very general and they need to be constrained to the parameter space of the event that we're trying to reproduce. This here is a computer simulation developed by my colleague Yuhong Fang, and again, not an observation, this is a simulation, and those colored lines are magnetic lines of force above two sunspots. And as new magnetism emerges through the sun's surface, it interacts with that pre-existing magnetic canopy, and it destabilizes it, and it causes this catastrophic eruption. It's a coronal mass ejection modeled. Observations also allow us to test the robustness of these models. Now, if models are able to reproduce observations, then great. Then we know that the physics in the model is probably telling us something about the physics in the sun. If models, on the other hand, do not reproduce the observations that we have, then we know we have to go back to those equations that drive those models and change them and find the physical ingredients that we need in order to really reproduce the things that we observe. Observations of the sun's magnetism at its surface are used to extrapolate and reconstruct that heliospheric magnetic field that goes out into space. The reason we do this is because it's really hard to do measurements of the magnetic field of the sun in the corona and out in the heliosphere. But we can use, with models and observations, we can actually reconstruct to some degree of accuracy that heliospheric magnetic field, which in turn is very important to understand the environment along which space weather events travel. And lastly, observations coupled with models are used to reproduce the current conditions on the sun and then evolve them into the future to produce forecasts. NOAA's Space Weather Prediction Center does exactly that. They issue daily space weather forecasts, daily space weather forecasts, I guess. And the problem is that space weather forecasting lies several decades behind the Earth's meteorological weather forecasting, both in the accuracy, the sophistication of the models and the accuracy of those forecasts. So there's still a lot of work that needs to be done in order to produce more accurate forecasts of space weather. We need, of course, more observations, but we also need better models to be able to forecast that better than a 50-50 chance of getting it right. last slide, well, kind of. I just wanted to say that whether we want it or not, we do live with this star. We live kind of in its not outer atmosphere, we don't live in the corona of the sun, but we live in the heliosphere of the sun. And because of that, we are subject to its winds and we are subject to its storms. And as our society becomes more technologically dependent, it's becoming more and more important to be able to predict the behavior of the sun and protect us and protect our technology, maybe, from the effects of those storms. And magnetism is at the root cause of space weather. So only by characterizing the evolution of the sun's magnetic field can we begin to predict the causes and the effects of these solar storms. And that's it from me. Thank you very much for listening so patiently. It's my way of saying that what I do is very, very important. You know.
If anyone has any questions, we can bring a mic around and have a few minutes for a Q&A.
Thank you. It was a great talk. Thank you. Is there anything similar to this whole setup with the magnetic and so on on Earth? I mean, nature seems to replicate itself. Is there anything that's comparable to what's happening in the sun?
I mean, yes and no. The Earth does have a magnetic field of its own. I'm not an expert in this. I'm not going to go down that lane very much. But what I think I know is that the sort of molten iron in the core of the Earth and its motion creates the magnetic field for the Earth. Now, they're very different in that the Earth's magnetic field is much weaker and it flips about every, I don't know, several 100,000 years, but not necessarily periodically. The sun's magnetic field, I said those sunspots vary on an 11-year period. The sun's overall magnetic field, the polarity, where north is and south is, that flips every 11 years. So you actually have a magnetic cycle that is 22 years long. You have north, this place, and south down here, and 11 years later they swapped, and then 11 years after that they swap back to their original place. And that process, we think we have a grasp on how it works, but there's still yet more work to be done in that domain too, to fully understand it. I don't know how it compares to the Earth's dynamo process that generates the magnetic field and makes it flip.
Thank you. Thank you for the talk. You answered part of my question there when you said the sun has poles, right? And because I noticed in that 1 month solar flare demonstration that it was coming mainly from east and west. It wasn't coming out of the top or the bottom. Was that why?
Yeah, so the sun rotates. Is that what you're referring to, that sun rotating? The sun rotates, and it rotates with about a 27-day period. And that is somewhat related to that generation of the magnetic field inside the sun. But then there's more complex processes that kind of make this magnetic field flip. But that rotation is certainly related to the magnetic field and part of the solar dynamo.
Thank you.
Thank you for a very good talk. I was curious about observations that have gotten into the core of the sun. What type of observations were used, or mathematics, whatever?
Oh my gosh, the core of the sun. So again, you catch me at a place where I don't know much. But we cannot observe the interior of the sun at all because there's no light that comes out from it, right? The way we probe some of the interior of the sun is the same way we probe the Earth's interior through means called seismology. The seismology, we see patterns of movement at the surface, we see how waves propagate in the surface, and we learn a little bit about the interior. Now, the core of the sun is too far inside the sun to even probe it with seismology for the most part. There's some seismology experts in the audience, but I don't want to put my foot in my mouth. But a lot of what we know from, well, first we know that the sun emits light, and the sun is generating all that light that kind of comes out towards us. And we know it happens because of nuclear reactions. And that's the only way to really sort of produce that energy output that the sun produces. We also measure, this is the only part that is maybe not remote sensing, we measure neutrinos that the sun kind of emits from its nuclear reactions. And we learn about the sun's nuclear processes through that too. But beyond that, I'm not going to say anything because I'm just going to be lying, and I don't want to do that.
Does the sun's rotation affect the solar winds?
Yes. Yeah, it does. And I didn't talk about that at all, but the sun rotates and it emits this wind. And this wind kind of like follows it in a spiral pattern throughout the entire solar system. So the sun's wind is kind of like, there's this, and its magnetic field, that heliospheric magnetic field, spirals throughout the entire solar system because of that sun's rotation. Good question.
Thank you for the talk. I just wondered about the Carrington event and
yeah.
how that compares with our solar maximum that we're in now, and if that
Yeah.
was a really anomaly, or if, you know, how does that compare?
So the Carrington event was a big solar storm, and to my knowledge, to the knowledge that we have, the intensity of that event has not been surpassed in the space age. There was one event that they think might have been bigger. It just happened on a different side of the sun, not looking towards us. We didn't feel those effects. They were seen by satellites that were orbiting around the sun. But I can't tell for sure whether that was bigger or not. It's certainly infrequent. The Carrington event happened in the 1800s. And it's not happened since, at least as far as we know. But it was a large magnitude event, and it's in the realm of possibility. The thing is that the Carrington event happened at a time where we were not as technologically dependent. The technology back in the day that got affected was telegraph wires and things like that, right? So wires on the ground that were affected, again, currents induced by those geomagnetic storms through telegraph wires that, you know, sent sparks and burnt telegraph stations or did what they did. But nowadays, I think we would be a lot more vulnerable to a big storm like that because we have a lot of assets in space, and space is less protected.
Thank you for the talk. I noticed on your chart the Maunder minimum,
Yeah.
which kind of coincides with the mini ice age of the great,
Yeah.
that cooling period. Do we have any theories on what caused the Maunder minimum?
Again, I'm not super versed in it. I've not heard anything conclusive about that. I don't know. The other question that's interesting about the Maunder minimum, so this was, let me show that graph for just a second so that everybody knows what we're talking about. That graph on the left, that sunspot record that goes back to the 1600s, is pretty consistent all the way down to 1700 or so. But before that, there was a period where barely any sunspots were observed on the sun's surface. And it's a period of like 50 years. So that spans, you know, several solar cycles where barely any sunspots were observed. It's called the Maunder minimum. We don't know why it happened. And we also don't know, we know that there were not many sunspots to be seen, but we don't know what all these other quantities that vary with the solar cycle did, because we didn't measure ultraviolet radiation in the 1600s. We didn't measure solar flares we had no idea what these things were. So there's a lot of questions about this, and I don't have answers, but there's people working on that, if there's any consolation.
Thank you for the talk. I'm pretty much a novice with the study of the sun, in that I see it every day. I hope that I'm out here. But can you correlate any activity with gravity in the sun? And gravity in the solar flares as they come out, but the gravity pulls them back in again. What is the relationship between the sun and gravity?
I'm not sure I can answer that question faithfully. I mean, the sun has gravity, of course, but it doesn't change like the solar events do. I don't know that there is any relationship, at least known relationship, between solar flares and gravity. These events are mostly caused by magnetism, not by gravity itself. Yeah. Yeah.
Hi, thanks for your talk. Most of the information we hear about sunspots is negative. It's affecting communications, it's doing damage. I have to believe there's something positive about it. As a natural phenomenon, it has to do something good.
Honestly, I don't think they're good or bad. They just are, right? A manifestation of the magnetism in the sun, essentially. If you want me to pick something good, I mean, sunspots in themselves are not good or bad at all. But the magnetic forces on the sun, and they tend to be concentrated around sunspots, are the things that allow solar storms to happen. But that doesn't mean that if you have a sunspot, you're going to have a solar storm. Not at all, actually. Most sunspots are pretty benign. A good thing about solar storms? Northern Lights. I mean, I was so excited to say.
I'm just wondering if there's like an emergency plan in case of a solar event.
You know, many years ago, I went to see the back then director of FEMA a talk at NCAR, and he was talking about space weather mitigation strategies. So yes, I don't know to what extent those plans are detailed or anything, but there's definitely both estimates of how bad a bad space weather event can be in terms of its financial cost, what we can do to prevent, to mitigate its effects before it happens, and what can we do in order to like recover after a big effect. Of course, small solar storms don't cause major problems, but a big one potentially could. And there are plans in place. I'm not privy to those plans.
We have time for one, maybe two more questions, if anyone has. All right, so there's going to be a QR code on the screen for NCAR for a short 3 to 5 minute survey about the efficacy of how successful this program was. If you wouldn't mind scanning it and taking that. And then also joining us in thanking the National Center for Atmospheric Research and Dr. Rebecca Centeno, and hope you have a great night. Thank you so much.
And thank you all for being here.